Thank you so much for giving me the opportunity to talk here today. I'm going to kind of delve a bit deeper into some of the topics that we've already heard during this workshop. I largely focused on aspects of magnetic fields, however, in some different ways than what we've seen. If you haven't met me before, I'm a new professor at some other institute of technology. I largely think about neutron-star mergers, but also about plasma effects and fluid formulations for relativistic systems. And let's just, start right in. So the idea of the system that we find ourselves discussing today is neutron-star mergers. We heard so much about them, exciting opportunities using Einstein Toolkit to model them, using MHD, neutrinos, equation of state. So what's actually left? What kind of in this picture haven't we heard about this week? And so I thought, well, I start with that something that people have not modeled very extensively, but that might be very exciting in the future. And this is what kind of other transients you might get from the collision of two neutron stars. And the name there is going under the name of precursor emission. The idea is that, as we've seen in Bruno's slide, if you put neutron stars before the merger with external magnetic hair, the hair can interact and potentially drive transients itself. This is before the two neutron stars collide. And if you wonder, well, what kind of things could happen there? Is this something that people have wondered about? Actually, yes, people have even thought to look for this in the context of gravitational wave events. This is one kind of trial search for binary black hole event. You don't really expect to see much there, but just to show that this actually works on the hardware side, this is for the W170104, where people use an all-sky instrument in the megahertz band in Owens Valley. This is a Caltech operated instrument with about 150 dishes, where they can do an all-sky search. And the idea is ideally you want to correlate one of those dots, if they exist, with a potential gravitational wave event denoted there with those components. And as you go forward, maybe it's not megahertz, maybe it's gigahertz. So in principle, you could also use FRB machines to detect this. What I actually want to motivate in the first part of this talk is that using simulations, not using Einstein Toolkit, but using AMRX, one can actually motivate that the gigahertz devices are very well suited to look for precursor emission. Okay, and for this, we kind of have to zoom out of the neutron star. We heard a lot about what happens inside the neutron star. We heard what happens at dense matter. We heard what happens, when you merge, you get turbulence, all of this. But for this part of the talk, we really, zoom out, ignore whatever happens inside the neutron star, and wonder what actually happens on the outside. And what neutron stars can have, if they have strong magnetic fields and you have either orbital motion or rotation of the star, is that you can trigger pair cascades. You produce a voltage gap at the surface of the star, you trigger a production of electron and positron pairs, and the entire magnetosphere fills up. And as we heard in one of the questions from Lorenzo, is the dynamics in force free can be very different than the dynamics in MHD, in the sense that this pair plasma may not behave the same as the matter inside the star. And interesting things can happen. Your magnetic field lines effectively get inertia. And so as the star is spinning around or is orbiting, the field lines, some of them will be closed, some of them will have to open up, and interesting things may happen. Now, what kind of precursor transients could you actually get? There's a variety of what people have investigated, largely on the same cartoonish level that I'm showing here. You could have a reconnection power transient that's the same as having a viscosity for a magnetic field. You convert magnetic energy into largely X-ray. You could have that your neutron star is like a hard-boiled egg with a shell that can crack. Once you crack it, you can release alpha waves that could potentially give you gamma rays. And there have been even recently some claims about precursor transients for gamma rays, and maybe this is this, maybe it's something else, who knows. You could have transients when the magnetic field, when the neutron star gets swallowed by a black hole, neutron star black hole merger, or later collapses. You could shed the magnetosphere. This can give you a transient. Or what I'll focus on today is if two neutron stars have hair or just one, then the interaction itself can already drive some traffic. And the interesting thing for this community here, I think, is that in terms of simulation, a lot has happened over the past decade. And basically, for each of these processes, run different sophistication, different types of simulations, and study what are actually the impacts of this. What are the impacts of flares? What are the impacts of alpha waves, binary interactions, or balding transits? And if you think in terms of this binary interaction here, so you kind of take Bruno's initial condition and you run this in the force-free electrodynamics code, you can ask what actually happens in this. And one of the things we were able to show a little while ago is that when you have two magnetic fields and they have some sort of misalignment in them, then in this highly conductive plasma, the magnetic field lines can connect, and relative motion in your orbit or even in the rotation of the star can transform energy from the orbital motion into the magnetosphere. If you want to see how this looks like in a simulation, we're kind of going to zoom in on this. And so you have the two stars, you have the connected field lines. In color, I'm showing the out-of-plane magnetic field. This encodes the amount of twist that is being built up in the magnetosphere. And now if you wonder what happens if you twist too much, well, there you go. So as the binary is orbiting, for every half orbit, you basically build up so much twist that you kind of inflate the field lines, they reconnect, snap, and you periodically eject those flares. And those flares are very interesting because when they interact with the surrounding medium, you can potentially power observable transients. Because the challenge here is not what is the energy of the flare, but rather how do you get it to something your telescopes can see. And the periodicity here is by definition milliseconds, because this is connected with the orbital time scale, and you likely will get this phenomena only in the final orbits. But let's look at some of the properties in more detail, because we actually did quite some parameter survey there to understand how likely is this a generic case, when would we expect this, and what would we expect to see. So prior to merger, if you have those two stars, depending on the degree of misalignment, you can get up to 20 of those flares that should be sufficiently strong to do something with your telescope if this happens, and if the binary is not too far away. Well, you can show using simulations that actually this will always happen as long as one of the magnetic fields in the star is strong enough. So it doesn't really matter if both are strong or not, really just that one is strong enough, up until you get to a ratio of about 100. The luminosity here is always 10 to the 43 octaves per second. If you're not familiar with those numbers, because hey, maybe they're too astrophysicsy or you come from a different area, if you look for fast radio transients with your radio telescope, 10 to the 43 is a good number. So this is roughly where you want to end up with. You need for this about 10 to the 11 Gauss. This is roughly on the upper end for stars. As you heard in Carlos's talk, there's like a population of stars. Younger stars have stronger fields, older stars have weaker fields, but 10 to the 11 is sort of good. And you can find that there is a scaling that goes with the separation and is about 1/3.1. The interesting thing now is, well, you could also do this using some pen and paper. If you do this with a pen and paper calculation, so why do we actually need to do computations, right? You're up by a factor of 100. So if you just do with a naive pen and paper calculation, you would be a factor 100 too pessimistic. So really numerical simulations are critical to do this. It's a good motivation to keep pushing on this topic. The other thing is, of course, what happens if you have a neutron star and a black hole. This is particularly interesting because most of the merging neutron star black holes that we expect to see with LIGO will likely not have any electromagnetic counterparts. The neutron star will just get eaten whole. And so this is one of the few transients you might expect to do something because matter is still left before the merger. Okay, and there we find, well, it's slightly more pessimistic. We find about 2 sufficiently strong flares if your magnetic field is 10 to the 12 Gauss. This is largely because you have larger separation, because for realistic mass ratios, the binary orbits at larger separation close to merger. This means that you twist lower field strength field lines, and overall your energetics go down a bit, but you could still get 2. And if you look at the energetics, slightly less, but still 10 to the 41 ergs per second. So this is still a promising mechanism. So really it's something that operates very generically when I'm showing you this kind of picture and movie for neutron star, and neutron star black. But now the thing I have not shown you, and this is the important one, is what would we actually see? Like which telescope would your observer friends have to point in order to observe this? And here we gain some really nice insight from the simulations themselves, telling us how you can convert this energy in the flare into observable radiation. So what you need to do is you need to track the flare further out, and really you need to model the entire ambience. It's basically the same type of problem that you have with kilonova. You have all of this material going out. You need to run nuclear network, optical transfer, yada, yada, yada. But here for this problem, what you can do is you can basically in the simulation see that there's kind of a close magnetosphere interaction that can directly convert this. And the idea is that you have closed and open field lines. The details are maybe a bit too much for this talk, but the idea is basically if you hit this region here, the spiral, something interesting will happen. And we were able to show this basically using a full 3D simulation. This is actually done using AMRX, where you have the flare getting ejected, the flare ultimately hitting the spiral structure. And when it does so, there's a microphysical process kicking in that on the centimeter scale drives fast wave emission, which ultimately decouples, converts into radio, and then gives you really a fast radio burst-like signal with all the properties, frequencies, and so on that you would expect. The only thing is that this thing is at slightly higher frequencies, and the details depend very strongly on what the configuration of the binary is. But it's really the first time we can use a simulation to kind of make that connection very robustly. Okay. That was sort of the physics side of this motivation. But now this is really a workshop on computation. So I also want to highlight a little bit of like what makes it actually hard to simulate this. What's the intrinsic challenge? It's a challenge that's common to all of the problems that we've heard here today. I just slightly present them in a different context. And this is the problem of scale separation. Naturally, all of these microphysical problems have different scales. In the merger, you have like the viscous scale, the resistive scale, and the microscopic scale. Here you have the same, where the emission is governed on some microscale that you can never resolve because it's a 10 to the minus 5 kilometers or less. You have at the same time the ergosphere, which is 10 kilometers if you have a black hole orbit, maybe prior to merger, where we typically simulate 50 kilometers, outer inner magnetosphere 200 kilometers, outer magnetosphere 1,000 kilometers. So you need tools to bridge this divide, and you need to do something about your microscales, which even with AMR you cannot resolve. Okay. And so one of the things that we do is we kind of limit ourselves on the physics. So we say, well, microphysics is one thing. We solve force-free electrodynamics. We try currently at Caltech to improve this a little bit by using different numerical methods to model this system. But for now, the idea is basically, can we do something in order to improve microscales in some form? And what we do on the numeric side is actually quite interesting. We solve the force-free system in flux conservative form, and we do this in a co-rotating frame. Because it turns out that all these features in the magnetosphere work much better if they don't move over the grid all the time. And so we use the co-rotating shift, everything basically stays in place, and then we simulate this. I've written a high order AMREX-based code, fifth order convergence, we know Z, implicit time stepping. You can solve these equations and you can kind of get all of this dynamics. One of the challenges that you have now when you want to capture your microphysics, this is using adaptive mesh refinement here, this is a slightly different problem. You launch a wave from the surface of the star, you adaptively track the alpha wave as it's propagating out, and you by hand put some more resolution here at the equator where you transit, you form a current sheet, you form these little microscales. Again, keep in mind, this is like 800 kilometers. This here is maybe like 100 meters or less. You want to capture all those scales at the same time, and really there AMR can help you to a certain degree. Then when you look at this in 3D, it actually looks quite pretty because you can really see that kind of this is an instability that grows. It grows in full 3D. You can see the merger of these little blobs and all. It's really nice. And there, I think AMREX holds a lot of promise. At the same time, you don't only want to improve your numerics, this is one thing, but you also want to improve your physics. Because really, if you want to include the microscales, there's no way you can do this for ab initio. You cannot brute force those calculations. And just like for some of those situations, you want a separate model for, let's say, turbulence, you also want a separate model for MHD microphysics. And there you can get inspiration by looking at other fields, because those are problems that's not unique to our community. Rather, other communities, especially like the space physics community, where they can send satellites to planets and see what magnetospheres are doing and get real data. And you can actually recycle some of the technology they have developed in a Newtonian context. And there, in this other community, heavy ion physics, they developed the same technology for very different purpose. If you kind of bring the two together, you have some very nice scheme where you can systematically, just like with M1 for the neutrinos, include all of your microphysics in an orderly way. And I'm going to show you how this works. The idea is basically rather simple. You have, from first principle, you have kinetic theory. This is your collisionless electron positron plasma. This you cannot study. For this, you need a full Higgs-Boltzmann code. Some people do this. It's very expensive. In GR, it's only been done in 2D so far, because one of those simulations costs like 10 million per hour. So it's something that's not really feasible at the moment. Hydrodynamics is something we solve every day, and many of you have learned during this workshop how this works if you solve it for the first time. So you want to do something that's maybe a little bit in between, kind of combines the best of both worlds. And one thing that in physics you always like to do, if something doesn't work, you say, well, maybe I can step epsilon away from something that works. So you can perturbatively add in those corrections. This goes under the name of dissipative hydrodynamics. Nuclear physics tells us how to do this in relativity, and you can exactly do this. You can at every order incorporate effects that don't bring you here where you want to go, but they bring you epsilon close. And so the way this works is that your typical hydrodynamics, which just has energy density, fluid velocity, and pressure, gets a correction. This corrections will have names, bulk viscosity, heat fluxes, and anisotropic stresses. So you have this pi guy, this encodes bulk viscosity, so this is resistance to compression. You have heat fluxes. This encodes how temperature gradients are included in your system. And you can also do shear viscosity, where basically your shear flow has some certain resistance, same as resistivity for the flow, and you can incorporate this as well. The challenge is this is not trivial to do in relativity, because those systems, if you do them in Newtonian, they violate causality. Like look at the heat equation. If you put some dye of stuff in water and you say, well, what's the fundamental solution? You see it's non-zero everywhere in space. at any time larger than 0. So really, in order to preserve causality, you have to do better. You need to preserve the wave-like character, and there are special equations that can do this that you would like to know. One example of where this comes in, if you want to know what's the actual application of this, is in the case of weak interactions for dense matter. In the neutron star merger, what happens is that those reactions initially balance. So you have neutrons go to protons and back. This is in your initially merging stars. Then, as you drive the system to merger, in principle, those reactions no longer balance because you change the temperature conditions and the density conditions. And then the feedback of those reactions on your matter, in principle, should give you some sort of bulk viscous feedback. So in principle, from first principle physics, there should be some intrinsic bulk viscosity in a neutron star merger. How large it is and what it does is sort of a different question. We looked a little bit into this using simulations, where the idea is there actual feedback? Do these effects exist in a neutron star merger simulation? Should we care? And the answer is yes, in principle, they're there. They very strongly depend on what the conditions are. The lower right here is a simulation of a neutron star merger, where we basically solve a two-fluid reaction system and then check how this equilibration feeds back. And in principle, if you're in the right neutrino condition, you get bulk viscosity. If you're not, then this effect gets suppressed. So this is, let's say, I would say interesting. It's kind of an application for what you need this for. The other thing, and this really brings us back to our initial point of MHD, how do you do this with magnetic fields? They make everything more complicated, and this stuff gets significantly more complicated if you want to include magnetic fields. Then you basically not just have the fluid dissipation, but you also have resistivity, you have Hall terms. The question is, do we need all of them? Because in principle, Hall effect is on much longer timescales than the merger. Resistivity, do we need this? In the magnetosphere, maybe. But the thing is, we can actually study it numerically. And the interesting thing is, we were able to write down 2 years ago a formulation of how you simulate those systems using exactly the same tools we use for neutron star mergers. And this is remarkable because in principle, these equations have the wrong form. So you need to massage these equations in a very specific way to make them work in astrophysically turbulent flows. You can do this, and if you do it, you can actually solve everything rather nicely. You can incorporate those effects. We demonstrated that this works with like a proof of principle in 2D. Now the idea is to extend this to dynamical spacetime and see what it does in a neutron star merger or a black hole accretion disk. But this is really kind of exciting because now we can have bulk viscosity, heat conduction, plus everything coupled to magnetic fields in a way that works with turbulence. Okay. Right. And one of the interesting things that magnetic fields here do, just to show a pretty picture, is if you have a heat flux and you have a magnetic field, the magnetic field gives you a preferred direction. This is less relevant for neutron star merger. It's very relevant if you're thinking about black hole accretion and event horizon telescope. Okay, there the conditions are such that the heat flux develops a very strong anisotropy. The electrons can basically only flow along the magnetic field line, but not across, because the electrons are tightly gyrating around the field lines, which basically means that if your heat conduction initially is isotropic, so it moves in all directions the same, in this limit, it would only follow the wavy field line pattern. This is a very different behavior than what you naturally expect, and we can smoothly transition through those regimes with those equations, which I think is interesting. And on the numeric side, what kind of enabled to do all of this is to actually extend those equations to have a well-defined Riemann problem, which allows us to solve this system completely flux conservative. This means even though you typically assume in your astrophysical system that yes, well, maybe there's a finite resistivity or a finite viscosity, but only in parts of the domain, and parts where there was viscosity is not resolved, we can basically capture sharp discontinuities in the viscous variables, just as we do for the hydro variables. This is very unlike things you see in heavy ion physics, where everything is just a diffuse gas and you don't need to do anything special. But for our applications, this is really critical. And so there's a lot going on here in order to enable those simulations. And then finally, to make one more comment, we actually even know today, if we wanted to do this for the force-free magnetosphere, we have to go to second order in those equations. Everything gets horribly complicated, but we at least managed to work out what the equations look like. And so we can now write down the relativistic system for reconnection, dissipation, flares in force-free magnetospheres using full two-fluid dynamics. So further down the road, I think what we will attempt is to solve the dynamics of electrons and positrons, and then see really how does that do if we have a full two-fluid code in relativity. But this is computationally more challenging than what we do today. So this is maybe more like for the next 2 years or so. And now going back sort of, okay, this kind of gives So a more exotic picture of what you can do in a neutron star merger, but where's all of this formalism actually relevant for the parts of the talk that we have already seen? And here I want to pick up one of the themes we had yesterday and today. This is about the short gamma ray bursts and jet launching. Where can we use those effective theories in order to get a better picture of what actually happens when jets are launched, or how do they launch in the first place? This is what I want to focus on now. And so there we heard in great detail, and we actually heard also in the next talk from Mikhail Shabanov, that during the merger, magnetic fields get turbulently amplified. I've heard about this from Carlos as well. You can create all of the small scale turbulence. You might get very strong magnetic fields, but can they actually lead to jet formation or not? This is something, as we heard, we may not be able to resolve numerically, but maybe there's some insights we can gain from dissipative theory, some kind of way we can get those microscales go back. And I'm not talking about Elias, but I'm really talking about putting in some of the magnetic field dynamics using dissipative formulations. And the idea is really that you want to have some effective way of including your microscales back into the global problem. One interesting thing we looked at with a former graduate student in Princeton was when you have a neutron star merger at very high resolution, this is some unpublished thing at like 40 meters or something, you see that you have here at the surface very small scale turbulence that begins to basically mix your outer layers. And we actually found, well, this might very well be a Rayleigh-Taylor dynamo, because you can centrifuge out matter, this gives you some mixing. And Valentin Skutnev worked out the entire dynamo theory for this problem. And now the idea is, well, if you have this, maybe we can just put it back in. So a very good understanding of the local problem, and you can reincorporate this. But how would you do this? How would you actually, fix this global simulation with under-resolved physics? How can you do this? And then the idea is to use insights from solar dynamo theory. Just as we said, there are under-resolved microscales in terms of viscosities for the fluid. There are also similar things in terms of magnetic field amplification. One of the interesting dynamos that popped up in the neutron star merger context in the past weeks in the literature that I want to highlight is the alpha omega dynamo. There, the idea is basically if you have a magnetic field line, you inject the current along this field line. So J is proportional to B, J is the electric current. Then what will happen is your magnetic field line will begin to inflate. And if you have a background shear flow, this is this omega, you can basically self-sustain produce colloidal field from a purely initially toroidal configuration. In other words, if you have a star, as we've seen in this movie by Bruno, where the field lines go around like this thing can basically make them bubble up, open up, and launch a jet from a star base. Okay, that's the idea. And this kind of mechanism, including this in simulations that don't resolve it from first principle, is something that's very common in accretion disk physics, galaxy dynamics, or supernova. And so what you can do is, if you say, well, I completely understand how two-fluid relativistic theory works, I can basically go in and derive how the relativistic version of this effect looks like. There's been something in the literature, but I think we can do a little bit better than this. And so if you do this, you can actually reincorporate this in a neutron star merger simulation. And this is very interesting because a few weeks ago, there was this paper by Ken Takeuchi, which said, well, if you do a 12-meter simulation of a neutron star merger, it looks like the outer layers sustain an alpha omega dynamo. So this kind of simple picture might actually be what happens at the outer layers of the neutron star. And if this is so, and if, as in their simulations, that leads to the formation of a jet-like outflow, well, why don't we just put this in all of our simulations? Okay. And so if you do this, I've actually done this earlier this year, you find some really interesting things. So here, this is kind of showing the same scenario of the post-merger. This is kind of my cartoonish star. There's a shear flow going on. If you actually look in the literature or in your simulation, what the shear flow looks like, and you see that the star, the stellar center, rotates uniformly. Then there's sort of this increase, almost looks like a boundary layer. There's some kind of maximum here. This is still inside the star. And then you have this Keplerian fall off at the outer layers. If on this background, you now include this alpha omega dynamo, which Kenta has found using these ultra high resolution simulations, you can systematically study how this gives rise to jet launching and outbursts. And so the idea is, if you do this, you get from those regions here, you can basically, using the alpha omega dynamo, induce a very strong magnetic field amplification. We did this for 2 cases, and then you can see what happens. And what we find in the simulation is that as the alpha omega dynamo switches on and starts building up colloidal flux, we see that the Parker-type instability that you see in the solar corona sets in. Little magnetic loops begin to stick out of the star. This is similar to Luciano simulations in some aspect. They begin to stick out. Then the shear flow begins to inflate them. And just like in the sun, if you want to see what happens is, you form these large extended loops over here. And ultimately, as if you remember from the beginning of the talk, if you twist too much this loop, it will explode and fly away. And you get the same situation as in a coronal mass ejection. And so what we're able to show is if this dynamo generates fields of about 10 to the 17 Gauss, you get periodic flaring activity from the post-merger remnant. And the same situation is actually something we also found in a related context in the magnetar flare scenario, where basically you could have an isolated neutron star, you have some activity at the surface, and you get similar outbursts. It's really kind of a universal phenomenon that may also operate in a neutron star merger. And then finally, what the interesting thing is, if you wonder, well, does this thing just periodically give outbursts? Well, at some point, when the differential rotation sort of gradually slows down, rather than just giving those flaring types outbursts, this is actually showing v squared over rho, and we get magnetizations of about 50 in the simulation, actually thanks to reprimand. That really made the thing stable. So this is actually very, very useful. If you do this, you get these periodic outbursts. And then finally, this thing starts building up a jet-like magnetic tower, just like a Lyndon-Bell solution, that ultimately also seems to show some signs of kink instability. And so the interesting thing is this could either power part of the GRB or the entire GRB. There's a lot of uncertainty here because we do have neutrino pooling, but not neutrino absorption. And even if we had it, it's not entirely clear if the neutrino-driven winds would not ultimately quench the power of the outflow. So this is something that we have not looked into, but other people have, such as Luciano and Philip Must. And then finally, I want to do, before concluding this talk, I want to do one more advertising slide. Just because microphysics is more than MHD, there's also nuclear physics, and especially because we have Roland here, I want to mention some work that's going on at Illinois. This has to do with how do we include more microphysics into neutron star mergers, and in some sense, how can we make neutron star mergers more like cosmic colliders? How can they systematically probe nuclear matter? You can actually, if you're curious, you can ask me about how you can do a comparison of neutron star mergers with heavy ion collisions. They are in some sense very similar, in some sense they're not. But one of the things you need to do this is accurate microphysics. You need nuclear theory in order to connect that through the merger with astrophysical observables via numerical activity simulations. And so the really kind of weak link here, apart from everything we've heard so far, is also how do you get the nuclear theory into your neutron star merger simulation? We say, oh yeah, there are some nuclear physics models available, some equations of state, you just download them, stick them in. But ideally what you would want to do, you would directly want to go here, you want to say, well, I changed some of the model parameters, how does that impact the neutron star merger? And if you could do this systematically with full finite temperature tables, this would actually give you very good control of how do these nuclear theory parameters get imprinted into observables. And for those who were here at Sebastiano's talk, this may be very relevant if you think in terms of next generation facilities where you could actually see the post-merger gravitational wave signal and ask things like, what about finite temperature physics after the merger? What about exotic degrees of freedom, such as quarks? And there, I think this infrastructure can help a lot, and I think this will be available very soon. Actually, ask Roland if you want a precise date, because he's one of the people writing.
Promise something working by the end of the year.
Good, great. So go to the website and check this out. I'll probably skip the proof of principle and keep up my summary slide. If people have questions, feel free to go ahead. Thank you.
We have some time for questions for Elias. It looks like we may have someone on Zoom asking.
No.
There's one in the room.
There's one over there, yeah. Several actually.
Oh, okay.
Yeah.
Yeah, so you've essentially also, I find this very nice talk and interesting. I wanted to ask you, comparing your magnetic tower outpost that you have with the alpha dynamo compared to what Luciano has presented earlier this week, you have super strong magnetic fields. How does do the energetics in the Poynting flux and in the emission compare in these both simulations?
Yeah, so what we have actually done, we run, well, first off, those two studies had very different kind of questions. We were looking at these very exotic kilohertz QPOs where you expect if this happens, you need extreme fields. What we did, however, is we cross-checked at lower field strength. And so what happens is then this flaring activity gets suppressed. but the outflow still sets in just at a later time. So there's basically, we only did this for 2 cases, so I cannot give you the full scaling, but there's basically a very clear suppression by at least 2 orders of magnitude in outflow strength if you decrease the dynamo action. One of the things that will come out later this summer is sort of a more systematic study of, like, also taking Kenta's results into account. If you systematically study this alpha omega dynamo, how does the jet power depend on this, or the outflow power, I should better say. But yeah, there's definitely correlation of like how much alpha omega do you have versus how much winding do you have, and then versus how much initial field do you have.
Very nice talk.
In those alpha omega simulations, have you checked for the conservation of helicity?
In the alpha omega simulation, we have not checked for the conservation of helicity. I've checked separately in a different simulation for conservation of helicity. Challenge is we don't have yet a good covariant gauge invariant formulation of helicity. So for those who don't know this, the EM sector has a conserved quantity. It goes like A dot B. Problem is it's gauge dependent. So we can definitely check, because we evolved the vector potential. We could check what it is in one gauge. Whether this tells you how good conserved it is a different question. Yeah. But yes, you're right, because alpha omega in principle needs helicity to grow. That's right.
There is an audio problem. I think it's okay.
Yeah, can I ask another question?
Yeah, sure.
Yeah, great talk. So many things to ask, but I will introduce myself. So going back to the first part of the talk of this precursor flares, you explore the parameter space, including different magnetic field configurations as well.
Right. So we explored we explored largely dipoles. We explored for one configuration also quadrudipoles. So it was motivated by this one nicer discovery with presence. So yes, we looked at something that's consistent with this. What you find is that once you have the quadrupolar structure, you can basically flare either with the dipolar or the quadrupolar part. And then it depends on sort of what's the relative alignment is. The only thing that may happen is rather than getting 2 flares per orbit, you may only get 1 flare per orbit in one configuration. When you flare with the wrong part, if you flare with the other part, you may get twice as many. So then it's more dependent on what the configuration is. Yeah,
I see. And so the other question might be a bit technical, but I was wondering if you have this gravitational field in this magnetosphere, in principle, you will generate things like, alpha waves with very low frequency, because the frequency will be associated with the orbital period. But you can actually show analytically that this will happen. But
you mean alpha wave just from
having 2 things
from the decay, or from interaction of the magnetic fields? So you just from the decay.
From the decay, also of the orbital. You can also show that having 2 things going around.
They should be emitted then around the orbital light cylinder, right? Because this is where you would have the inertia and where you would shake them.
Right. And have you checked that?
We have not checked this because those simulations are at fixed radius. What worries me slightly is, this is what makes this neutron star black hole so energetically disfavorable, is because there everything is dominated by stuff that happens at the light cylinder, at the orbital light cylinder.
Yeah.
And this suppresses very strongly anything that you can get, because what makes a neutron star so interesting is that you basically flare in between the stars. You flare at higher field strength, whereas there you flare at lower field strength.
Yeah.
So I have not checked, but my expectation would be that you launch a bunch of low energetically alpha waves directly on open field lines. I guess you would not open up field lines.
Right.
So this typical scenario of like how you explain coherent radio X-ray or something probably wouldn't work. Like you would not steepen them sufficiently, I guess.
Okay. Can I ask one more?
But there's one on the chat. I was wondering if you could scroll up there.
Oh, yeah, sure.
It's just just scroll up a little bit. There's the question right there.
There was a question. There was a question.
It's right here. It says, my question has to do with the pre-merger EM flare
question. Could this effect be seen in accreting supermassive black hole binaries? I guess there it would depend on if you would be able to get sufficient flux separation. So if you have the 2 black holes And you would either, I mean, of course, you can also get a coronal type setup where the magnetic field from the disk gets stuck in the black hole. But in terms of getting something in between the black holes, I would assume you'd basically need to get flux separation such that you have one polarity of flux in one black hole, the other one, the other black hole, so probably transiently change, and then maybe, yeah. But that's a good question.
And Scott, did you have a question?
Yeah.
I think we have time for one, yeah. Oh, is there?
Okay, then let's try later.
In the alpha omega dynamo jet, so there, post merger there's a lot of debris. Is this powerful enough to clear the debris?
Yeah, that's basically the open question. So here the scenario was we wanted to see if there's an imprint from the post-merger oscillations into the outflow. This would happen only very shortly after the merger. At this point, you have a little bit less bit of debris, and then the field strength, if they're very strong, they basically clear out everything. But what is not clear is if you had this at a later stage, or you had very strong neutrino-driven winds from the surface, it could be that the flares may either get completely suppressed, or if you get this tower structure, that the energetics is strongly suppressed. Yeah, I think this is the open problem there.
Yeah,
that's right.
Any other questions? Time for me one more.
I was going to ask, like at the end you mentioned connecting this to gravitational wave observables for next generation detectors. So for like, because there are speculated phase transitions, which normally we try to measure from the spiral part, but in the high temperature part of the binary neutron star mergers, like, does this vary the parameters, or is it computationally tractable to vary the parameters enough to like measure phase transitions from the bulk viscosity coefficients? Or
oh, you think in terms of something like phase conversion dissipation, if you dissipate strangeness or so from bulk viscosity?
Because if you're able to measure the viscosity, like maybe also at what order of like gravitational wave.
So one of the challenges with the bulk viscosity is that unless you're in this regime where you can convert a lot of neutrons into protons, or depending on what your equation state is the other way around, you basically get an effect that is of the same order as thermal effect. It's like 100 hertz at most. If you are in a neutrino trapped regime, which probably most of these systems are in, then this effect gets strongly suppressed. What I don't know is if you could actually form the phase transition, if you could sort of get the secondary change from that. But if you actually form like a stable hybrid star, then you get a signature from that alone that would probably dominate it. So it's not clear, I would say, but it might be a secondary.
Okay, well, thank you, Elias.